Now let us consider the height of an AVL tree. So what should be the height of an AVL tree? The proposition says that the height of an AVL tree T storing n keys is at most some constant into log of n. So we can have an AVL tree whose height is at most log n, which is written as big O of log n. We want to prove this, the height of an AVL tree is not or no longer than order of log n. So how do we prove this? The easiest way to approach this problem is to find the n of h. What is n of h is given in the below line. So let us define this quantity as follows. So what is n of h? Capital N of h is nothing but, n is nothing but number, okay, minimum number of nodes in an AVL tree of height h, okay. N of h is nothing but, let me repeat, minimum number of nodes in an AVL tree of height h. Now let us take an AVL tree of height h. So we are going to fix the height h, and then among all possible AVL tree whose height is h, we will take the AVL tree which has as minimum number of nodes in it. The meaning is that, for example, if we take an AVL tree of height 1, okay, so this is height 1 node. What is the minimum number of nodes that it could have? Only 1. Okay, what is the maximum number of nodes that it could have? That is also only 1. This is n of h, okay, which is nothing but n of 1, of height 1 is nothing but 1. Fine. Similarly, let us define for AVL tree of height 2. Okay, so let me erase this. If we want to have, so now let me fix the height. So I want to have an AVL tree of height h equal to 2. So we are going to fix the height. Now my n of h is nothing but n of 2. My height is 2. What is the minimum number of nodes that I can fill of height 2? Okay, so the minimum number of nodes that is possible, only this kind of tree. Okay, either this is possible or I can have this as in the left subtree. Okay, what is the maximum number of nodes that I could fill? Root, left and then right. Okay, but I want the one which is n of h, which is minimum number of nodes. So the minimum number of nodes that is possible of n of 2 is nothing but 2. What is n of 0? N of 1. Height 1 is nothing but 1. Okay, these two are the base condition for us to prove that the height of a AVL tree of minimum number of node is log of n. So the claim is that you take, so this is the bad tree, right? In the BST, this kind of tree is the very bad kind of binary search tree. So we are trying to take the worst case binary search tree and then try to prove that the height of such worst case binary search tree is log of n. Okay, if we try to prove for the worst case, the best case is also true. So we are trying to take such a bad AVL tree, okay, and then we are trying to prove that bad AVL tree, that what is bad AVL tree? Every level we can have minimum number of nodes. That is the worst case AVL tree, and in the worst case situation, that AVL tree is maintained its height of log n. That is what we have to claim. That is the claim, and we are going to prove that by setting up the mathematical function. Let us continue. We have already seen that for an AVL tree of height h, of height h, for h equal to 1, the number of nodes is nothing but 1. So we have already seen. For h equal to 2, okay, of height 2, the minimum number of nodes that it could have, an AVL tree can have as 2. So 2 nodes are possible. For h is greater than or equal to 3, an AVL tree of height h can have or contains one root node, okay, one subtree of height h minus 1, okay, it should have one subtree of h minus 1 and the other subtree of height h minus 1 or h minus 2. Okay, so let me elaborate this, why this is true. Now let us consider a height h equal to 3. Okay, we fix the height of an AVL tree and then we are trying to find out what is the minimum number of nodes that we could fill in that given height. Now this is the binary search tree of height h equal to 3. But this is not an AVL tree. So we cannot choose this as an AVL tree. Why? Because we have already seen that the balance factor for the leaf node is 0. Balance factor for this node is minus 1. However, the balance factor for this node is minus 2. So this BST is not an AVL tree. Okay. So we cannot have a tree whose height equal to 3 in this fashion. Okay. I hope you understood. Why? Because this node violating the property of an AVL tree. So what we could have is that we have to have, so in order to make this node as balance factor maintained as required, we should have one more node in the left subtree. Okay, so this is of height equal to 3. Now you can see that this is satisfy the requirement, the balance factor is satisfied over here because it has the left subtree 1, it has the right subtree 2, 1 minus 2 equal to minus 1. But we want, among all possible AVL tree, we want the one which has the minimum number of nodes. Okay, I think this is the one which has the minimum number of node. Why? Because at this node, okay, I can also fill one more node. Okay, here also I can fill one more node, here also I can fill one more node. But this is an AVL tree which has the maximum number of node. But according to our definition, n of h, you recall, n of h should be the minimum number of nodes that it should have. So you pick up an AVL tree which has the minimum number of nodes in it. So a minimum number of nodes that is possible is only this. Okay, so now let us generalize this from this statement. An AVL tree of height h, okay, contains one root node. This is not at all an AVL tree. Now let us consider, when you go for height equal to 3, one should be a root node. Okay, and then one subtree should be height of, this is for height h. Okay, for height h, one left subtree or one subtree should be of height h minus 1, because its children cannot have the height more than h minus 1. Okay, so one subtree of height h minus 1. So we fix that if one subtree is have height h minus 1, okay, what is the possibility of the other subtree? So it can have height h minus 1 as we did here. Okay, h minus 1, this is h minus 1 or h minus 2. What is h minus 2? H minus 2 is this. Okay, that is what we are here. The other subtree can have an height h minus 1 or h minus 2. If we go to h minus, this is h minus 1. If we have h minus 2, then we can fill the other extra nodes, but we do not want that. Okay, so since we need minimum number of nodes, we have to choose, once we choose one of the subtree as h minus 1, the other subtree whose height should be an h minus 2. Why? Because we want the minimum number of nodes in an AVL tree. Okay, so let me generalize this. So if we choose one of the subtree whose height is h minus 1 for an AVL tree whose height is h for the generalization, or h equal to 3, one can have height h minus 2 which is h minus 1 which is height is 2, the other can have h minus 2. Okay, although we can have h minus 1 in this left subtree, we will choose h minus 2 because we want to maintain the minimum number of nodes. Okay, as the height is reduces, the number of nodes that we are going to insert is also reduces. So this is the one required according to the definition that we are going to prove. Okay, so what is n of now from this I can write what is n of h, which is n of 3, is equal to 1 2 3 4. Okay, 4. Now let us generalize. This is for n of 3. I have given n of 3 equal to 4. I have already defined the base condition n of 1 equal to 1, n of 2 equal to 2, and then n of 3 equal to 4. So from this definition we can generalize an AVL tree of any height h. It should have one root node and then it should have one left subtree whose height is h minus 1. Okay, so it is not a left subtree, one of its subtree is h minus 1, the other subtree is h minus 2. Okay, it is one lesser than this. So this is possible, or we can interchange. This is also possible. Of height h, it should have a root node, and in the left subtree it can have h minus 2, and in the right subtree it can have h minus 1. Okay, any of these are the possible AVL tree whose height or whose number of node is minimum. Okay, whose number of node is minimum. Okay, from this I can write what is n of 4. So how can I write n of 4? N of 4 is nothing but n of 3 plus n of 2, okay, plus the root node 1, right? So what is n of 3? 4, n of 2 is 2, and then plus 1. So we can have 6 plus 1, 7. Okay, so when we go for an height equal to 4, I can have the minimum number of node equal to 7. Similarly, I can show for this height equal to 3. So same formula. So how can I write? With the same formula, n of 3 is 4. How I can show? N of 3 equal to n of 2 plus n of 1 plus 1. And note down, these are the base condition. What is n of 2? N of 2 is 2 and n of 1 is 1 and then plus 1, which is 4. Okay, so we can generalize for any height whose minimum number of node is given n of h. So from this we can write a general mathematical function. So now let us recall, if this is an AVL tree and which satisfies the minimum number of nodes in it. Let's say let us take the one of its left subtree or one of its, okay, it is possible to have any of the side. Let us have this is h minus 1, and this subtree can have an height h minus 2, and this one node we should count, that is root node for that subtree. Okay, so I can write a general formula or mathematical formula as n of h. For any h, n of h is nothing but minimum number of nodes that is required, minimum number of nodes of an AVL tree whose height is h is nothing but n of h minus 1 plus n of h minus 2, okay, n of h minus 1 plus n of h minus 2 plus this node, okay, root node plus 1. So how do you count? So what is n of h? N of h is nothing but the minimum number of nodes of height h. What is the minimum number of node of height h? The minimum number of node in the left subtree whose height is h minus 1 plus the minimum number of nodes in the other subtree whose height is h minus 2, okay, plus 1. So when we solve this, we can get the value of minimum number of nodes whose height is h. So this is a general mathematical formula which is also known as recurrence relation. Okay, this is called as recurrence relation, and we are trying to solve this recurrence relation, but we are not going to solve this recurrence relation directly, but we will try to solve this some approximation method.